Okay, hi, I'm Jess and I'm doing the presentation on the power base. So as we look for future exploration and colonization on Mars, the key to ensure sustainability arises predominantly from the ability to provide a constant, reliable power generation facility which can be modular and is expandable. So today I'll be introducing my ideas about a modular power base station which is specifically designed to withstand the harsh Martian conditions. The system isn't solely about energy generation in the short term, but about creating a reliable, renewable, efficient power infrastructure that can support long term missions and eventually a permanent living habitat on Mars that's independent from Earth. So, the areas I'm going to cover today is the internal design, the challenges due to the harsh Martian habitats, power generation sources and the distribution, a brief overview of life support systems, including MOXIE, the astronaut training and role aspect, and their power consumption and the daily needs and weekly needs, and then protocols, and then a summary of the development targets. So for the internal design, level one, so the power station base is split into three levels: level one, level two, and level three. So level one consists of the nuclear small modular reactor unit, the charging for robots and exploration rover, thermal regulation, battery storage and emergency supply storage, the kilopower terminal junction, and the pathway around the facility, which is shown by the pink colour in all three levels. So everywhere has easy accessibility and it's colour coded. Level two, so again, you have the access around the facility where, like, the pink colour. So in level two, you have the automation AI monitoring unit, critical facility, the control area of exterior uses and designs like MOXIE, the greenhouse, the maintenance lab, and then also the turquoise around the outside, which I'll come to later, the solar panel retraction and cover zone, which is an experimental part of the power base station. And then onto level three, you have the habitat and living sector, which is the bottom part, which consists of female toilets and dormitories, and then male toilets and dormitories, which are shown by the sort of replica, almost symmetrical sides, research labs, power grid distribution system, and then the blackout control, safety, and communication room. So challenges facing energy on Mars. One of the main challenges, Mars has a very thin atmosphere, which is 95% composed of like 95% of CO2, which is no weather systems like Earth, which can be replicated. So there's no natural energy systems. There are extreme temperature changes. The temperature can fluctuate and drop to as low as 125 degrees at the polars, like polar ends. And then also solar energy is limited due to long Martian nights, harsh weather conditions like dust storms, and also the fact that Mars is very far from the sun. So moving on to the four main generation power sources. So the small modular nuclear reactor, which is used to power life support systems and habitants within inside the base. The solar power to support that, and the kilopower reactor, which is to power the main experimental purpose of my power base station, which is trying to make geothermal energy a reliable source for the future. So geothermal energy, the geothermal drilling unit, which I'll talk about later, is the main experiment, which also will require a significant amount of energy. So currently it's not a power generation source, but within 10 years' time and in the future, it's hopefully going to be the main power generation source, as it's so much more reliable than solar, as it's not dependent on weather changing conditions. So first we have the primary source currently, which is a small modular nuclear reactor. So its aim is to provide a high density power source, which would be essential for periods where solar power is unavailable for long periods of time, like Martian nights or long dust storms. So the advantages of using this is that it's compact and scalable. So it can be it has to be transported from Earth, but it can be transported in a compact space. So it's more easily deployable. It's much safer compared to traditional larger reactors, which it will need to be, as the small modular reactor is inside the power station base. And it also can generate consistent power without the need to be refueled for 10 to 20 years. So it's quite self-sufficient, which also gives enough time for hopefully the geothermal energy generation project and the unit to be running efficiently to then when it can take over from this. So the aspects to consider, the first aspect is the size. So the entire reactor core system, including the core, the heat exchange, the cooling systems, are around 3 to 5 meters in diameter, which is shown as they fit inside the facility on the base level. But they weigh 50 to 100 tons, so it's very space efficient. So the next part is the fuel, so high SA, low enriched uranium, known as HALEU, so it will be used. So the fuel is enriched with about 19.75% uranium-235, and this has a much higher power density than conventional uranium fuel, making it more efficient. And then the next aspect is a cooling and heating system. So it's possible to have a helium gas cooling system, as helium is inert, so very unreactive, and it's therefore very suited to high temperature operation and low pressure environments, like which are the Martian conditions it will be working in. Moving on to the heat exchange system. So you have heat exchange from the heating system. So heat is generated in the reactor core and is then transferred to a secondary loop where the heat is used to generate steam, which would drive a turbine, creating a turbine generator system. So we have similar things right now that work like this on Earth, so it can almost be replicated. And the turbine generator system will be used to provide energy to the living quarters. So the steam turbines here are utilising the fact that the SMRs, which is a small modular reactor, operate in the thermal spectrum, so therefore converting the heat into electricity, so the system is more efficient. So then you also have the deployment and maintenance aspect, which includes the launch and transport, and then also the maintenance, the general maintenance. So the launch and transport. So the reactor unit is launched in modular and in compact form and delivered to Mars, possibly via a lander. And then the reactor can be assembled on site by the robots, but if human intervention is needed, it can also be easily assembled by the human crew. So in situ manufacturing can also step into this. So once established, the small modular reactor unit, 3D printers and local resources could be used for repairs or spare parts or mini bits which are faulty. So for example, Mars regolith could be used for radiation shielding around the outside, possibly, so like utilising the resources that are accessible to us from Mars. Then moving on to the maintenance side, so you have mainly robotic maintenance, which, given the harsh environment, reactor could be equipped with robotic systems for monitoring and conducting base maintenance tasks like cleaning, heat exchangers, and then also there's predictive maintenance, which is the AI systems which monitor reactor health and then could detect any potential failures or radiation leaks. So it allows the reactor to operate smoothly without frequent need for human intervention, which is obviously a lot safer as well. So then moving on to the power output and efficiency. So the power generation, so over the span of how the small modular reactor would last, it would roughly generate 10 to 30 megawatts of electricity, which would be sufficient to power the entire base over a span of 10 years, and it's including powering life support, research equipment, habitat heating and rovers. And then the power output is going to be scaled, could be scaled for when it's modular and expanding by adding multiple units to the Martian power grid to allow for more distribution. So shielding, radiation and radiation protection. So due to harmful radiation coming from the Mars environment and coming from the reactor, the water and liquid hydrogen system can line the reactor around the outsides, which would not only operate as a shield, so to prevent radiation from being emitted into the base, but also to act as a cooling system, so it has a multi-purpose use. And then finally, you have the safety systems. So the reactor would rely on passive safety mechanisms to enable it to shut down automatically in the event of an emergency, like without human intervention, such as a radiation leak or spillage. And then the temperature detector on the surface of the cooling system detects that if the temperature has exceeded a certain threshold, it triggers the reactor to automatically reduce its fission rate. So when the temperature exceeds the threshold, it also triggers the start of the natural convection system, cooling system around the outside, which can remove the heat without need for pumps. So it allows the reactor to cool down immediately if it starts to overheat to prevent failure. So yeah, that's it for the small modular nuclear reactor. So then moving on to solar power, there are two aspects. There's the solar array field, and then also solar panels which are around level 2 of the power-based facility, which are mainly there for experimental use. So solar power cannot be the main power source, as it's not reliable enough to ensure a sustainable power supply for the base in the future, because Mars only receives about 43% of the sunlight Earth does, and it is affected heavily by extreme weather conditions and weather changes. So the aim is to eventually convert to geothermal energy and use solar energy, any energy that can be obtained from solar, to be stored in case of emergencies. So the first aspect of the solar power generation is from the solar array field, which is a diagram in the top left. So the solar array field is not directly connected to the facility. It's large adjustable solar panels which are tilted to minimize dust accumulation and can rotate. It has an automated cleaning system. And the solar panels have electrostatic dust shields, which prevents dust buildup by generating electric fields to break up the particles. And these solar panels will also have a transparent coating of the polymer Teflon, which will have to be transported from Earth, as it cannot be produced in the power base station. And the Teflon polymer, with the transparent coating, will block UV light and preventing harmful radiation to the panel, but to the solar panel, but still allows sunlight to pass through. The second aspect is the solar panels around level 2 of the actual power base facility. So these are at a slightly higher altitude on the sides of the power station. So because they're at a higher altitude, this possibly could lead to an increase in energy efficiency, as better sunlight will be hitting it. This will also help for detection of dust storms, as a detection and decrease of production of solar energy can alert our system that a dust storm might be coming due to like a drop. So then, because it's attached to the side of the facility, this allows us to retract the solar panels flat against the facility, which were originally at a diagonal like 45 degrees to try and optimize the sunlight. So if a dust storm or a decrease in power generation is detected, they can then be adjusted to lie flat against the facility and trigger a protective cover of reinforced titanium alloy to emerge around the outside of the panels, which means the solar panels are not only protected and do not become damaged during the dust storm, but they also allow extra protection and support to the facility during extreme environmental changes, which would minimize the chance of any damage to the facility. And the area, so if on the level 2 base design, there's the turquoise area surrounding the facility, which is this area for where the titanium alloy would be stored, and the solar panel contraction and retraction zone. So the solar panels attached to the base directly are also for experimental use, and also can be fixed easily if damage occurs due to their accessibility. These solar panels, the experimental use is that they will have photochromic layers which adjust transparency based on light intensity or radiation exposure. So if these prove to be successful and effective, then possibly this photochromic layer could be used on the outside of the greenhouse facility to like maximize food and water efficiency production. So the example of how the photochromic layer works is the diagram at the bottom. So if you look at figure 1a, you have the energy diagram of the photochromic organic solar cell. So the photoactive layer is a ternary blend, which is like 3 refrigerants, which contain a photo-switchable dye, which is the DAE, open, and an organic donor and acceptor, which is semiconductors for whole, so like which is the poly-TPD, and the organic and the electron transport, which is shown by PC61BM. These work similar to like electrophiles and nucleophiles in chemistry. So for example, when you're trying to produce a haloalkane from an alcohol or vice versa. So then the actual structure is shown by figure B of what happens. So after switching the DAE dye with the UV light from the colourless open ring, um, the coloured closed ring isomer, which is shows the absorption of visible light, which generates holes on the donor and the electrons. So the donor is what that donates the electrons on the acceptor, which is the like electrophile, which takes the electrons. So then the structures of this happening are shown by the DAE dye and the poly-TPD. So the DAE closed so from the DAE open to the DAE closed when UV light. So then moving on to the next aspect, which is the geothermal. So this is a main experimental focus of the base, as geothermal energy production will be needed to ensure a sustainable base on Mars. So the advantages if this can be up and working and running efficiently and self-dependently is that it's a constant power source. Unlike solar, it will operate 24/7 and is not affected by harsh environmental changes or conditions. It has a very small footprint, which meaning there is less infrastructure, less maintenance, less exposure as it's under the ground. So then our closed loop is of carbon dioxide, which runs around the facility of the geothermal drilling unit, reduces water dependency, which means there are zero emissions as it's a closed loop. You've got underground safety, so equipment can be buried and shielded from radiation as it's under the ground. So then there will be no extra protectants needed to prevent radiation from causing like harm or destruction to any of the equipment used. And then finally, if Martian geothermal energy can actually be accessed, are able to utilize the planet's heat through conventional heating. So the low average surface temperature, which is minus 63 degrees, can be survived then using geothermal fluids, which increase by like 30 to 50 degrees. So the main challenges, you have the drilling techniques, which are Mars's a very hard layer of regolith, which would be very easy to damage, like the drill heads and like drilling techniques that are currently used on Earth. There's also a problem with water scarcity. So geothermal needs a vast amount of water. If you use water as a source, you can also use carbon dioxide, which I think would be more sustainable. But the water systems, if water is used, would have to be very efficient before drilling even begins, which might take time to actually build up to that point. There's a low heat flow, so outside volcanic or areas and seismic areas, Mars' internal heat is lower than on Earth, so only specific regions may be viable, and we'll look into how some of these regions have already been detected on the next slide. And then finally, another challenge is automation. So the systems would need to operate with minimal human intervention, as humans can't get down, it's not accessible. So it'd have to undergo reliable autonomous drilling, and maintenance is essential to keep it working and running smoothly and efficiently. So on to locating the most sustainable areas of extraction. So you have the places of geothermal. So Mars has the largest volcano in the solar system, Olympus Mons, and it has large areas of volcanic regions, which are shown by the red on the diagram. But some of these volcanic regions have proven to be dormant, so for a sustainable energy production on Mars geothermally, extraction must be done in the ground. But this could also maximise the fact that Mars has a very thin crustal zone, so drilling into the ground might not be as difficult as it is on Earth. So regions of extraction, so specific regions of Mars have very high seismic activity and have already been detected, so these areas could be targeted. We could investigate more into Martian earthquakes, determine more reliable patterns in which seismic activity occurs, to then predict and adapt the area to the region we can construct the geothermal drilling unit in. And then the drilling, so the southern polar cap, the polars, which is shown by the blue on the diagram of Mars, is surfaced with layers of frozen carbon dioxide. So instead of using water as for the closed loop system, carbon dioxide could be taken from here and also condensed from the atmosphere, as the atmosphere of Mars is 95% composed of carbon dioxide. So this carbon dioxide could be condensed to inject into the hot rocks of the drilling in order to conserve water, which means we can create a closed loop and carbon dioxide system which minimizes the use of water and makes it more sustainable for the future. So then on to looking at the previously detected areas of high geothermal potential energy. You have the three main regions, Tharsis Ridge, which is the main, shown by the main area on the diagram that's red, and has almost the most annotations around it. So if you're looking at it, it's slightly from the middle, it's slightly shifted to the right. That's the Tharsis Ridge. You have Valles Marineris, and then also Elysium Planitia, which is near Elysium Mons. So Tharsis Ridge have massive volcanic regions, so high geothermal production. Valles Marineris is a system of canyons that run east in the Tharsis region, so it's within the Tharsis region, and it has geological rifts which may expose subsurface heat more readily and easily. And then also Elysium Planitia, which is near the InSight mission site, which is already being utilised by NASA, which is known to subsurface heat flat terrain. So moving on to how geothermal energy would actually be obtained. So the compact geothermal drilling unit. So the main components are the drill heads and drill types used, the casing system, cuttings removal system, the actual power generation system, the robotic deployment platform and how it's maintained, the downhole sensors, and then the geothermal converter. So regarding the drilling part, you have three drilling types used: the rotatory drill, thermal drilling, and laser drilling, to try and maximise efficiency. So the rotatory drill head, which is the main drill head that's used for the majority of drilling down, it's made of PDC, which is polycrystalline diamond compact, which is shown by the diagram on the top right hand corner. So it's very efficient and reduces wear on the actual drill. So it would have a downhole electric motor, which reduces torque stress on the surface and helps to provide additional power to the drill bit, which also includes the WOB, which stands for weight on bit, which is the amount of downward force exerted by the drill bit during drilling operations. So this will be achieved by actuators, which are devices that are already previously used, that convert energy into motion or force due to Mars's lower gravity. So this will be needed. And then the cooling system will be via the carbon dioxide gas circulation for this specific drill component from the Martian atmosphere that can be compressed. So moving on to the thermal drilling aspect. So it will have a resistive heating plate around the drilling bit, which acts as a heating element. And this will be used when the drill comes into contact with icy regolith or frozen rocks, so where it will vaporize or melt the substrate for easier removal, to prevent wear on the rotatory drill head or damage to it. The water vapor, once it's heated, once drilled through, then will recondense and be ejected to make sure it doesn't reharden and then almost damage or fix the drill in place so it can't be operated as smoothly. And then the drill heads can be easily swapped by a telescopic extension of the heating module. Moving on to the laser drilling module, which requires a lot of energy. It's a high energy pulse fiber laser that will be used. And the high energy requirement is going to be met directly by an onboard nuclear generator. So this laser will be used when faced with abrasive surfaces, ultra hard rock layers, which the rotatory drill cannot get through, or it would cause a lot of damage if it did try to get through. So the advantages of using this is that the laser has no mechanical wear and also has high precision cutting. So if there's a really small area that is just very hard, you can directly cut just with the laser that part. So it allows for accuracy, and also because it's more accurate, even though it requires a lot of energy to use, it doesn't need to be used over a large surface. So moving on to the casing system, the next component of the drilling unit. The casing system is going to be made from monolithic titanium alloys reinforced with carbon fibres. as this material has high strength to weight ratio, so it's very energy efficient. The material also has high corrosion resistance, high specific strength, high fatigue resistance. But the main reason for using this is that all of these components, all of these properties of this material are unaffected by high temperature and high pressure and complex stress environments, because if aluminium alloys or magnesium alloys were used, they all, under standard conditions, normal temperature, have the same properties, like high strength to weight ratio, and have high specific strength. But as soon as the temperature increases, the aluminium alloys and magnesium alloys, these properties are no longer maintained, but still under high temperature and pressure, the properties within the monolithic titanium alloys that are reinforced with carbon fibre still maintains these properties. So these come in about 1 to 2 metre segments, which will allow for autonomous assembling and disassembling, which is also easier for transportation. So the next component of the drilling unit is the cuttings and removal system. So compressed carbon dioxide from the Martian atmosphere, injected with jet filters, which can be integrated into the drill head, and then a suction pump to remove the molten material that's created from the thermal drilling from melted zones, to ensure it doesn't harden and to make sure it doesn't try to trap the drilling unit under the ground. So the next aspect is the power system. So the power system will rely primarily on the kilopower nuclear reactor unit. So the backup power system will be from backup generators, possibly lithium-ion battery packs, which will only be used as an absolute last resort. Thermal storage will come from PCM, which is phase change material, which its reservoir stores excess heat, so drill unit can still be used during the Martian night, so it allows for it to still run through pretty much all weather conditions. However, if obviously power generation, for example solar, which is affected by dust storms or long Martian nights, so if there's a decrease in power production, the actual power base, like the life support systems, the habitants, take priority over the geothermal drilling unit. So if there's a really low power supply, the geothermal unit will be the first thing that stops running, and the energy will go to the critical facility units and stuff like that, to prioritise obviously the human health, which is more important. And then moving on to the next aspect of the components of the drilling unit, you have the deployment platform. So this will consist of a robotic arm for drill string assembling and module switching. So you have AI control from onboard autonomy within the monitoring unit in level 2, which has remote override, so the humans running it can override any changes that the AI systems make. So a chassis, a leg lander with auto leveling, which is shown by the diagram in like the bottom middle. So it's a leg lander with auto leveling, and it will have anchoring feet for counter and force. So during the drilling, which is crucial as due to Mars' low gravity, for it to remain stable, this will be needed. Then onto the downhole monitoring. So we have temperature and pressure sensors every 10 meters down, which is a mini seismograph to analyze underground structures, which can be reported back to the control center. So then also spectrometers for any useful mineral detection, which could possibly be then extracted from the Martian surface and analysed to see if this can be used for human health, or minerals that could be used for other things on the base. There will also be a fibre optic cable that runs down during the drill strings for real-time data and laser power transmission. And then finally the geothermal converter. So once the target to reach down originally is 1,000 meters. Once 1,000 meters underground is reached, a heat exchanger pipe can be inserted to inject carbon dioxide into the hot rock and draw out thermal energy. So the heat turns the carbon dioxide into supercritical CO2, which is then connected to a thermoelectric converter, so a Stirling engine, which is already used by NASA and has already been sort of infiltrated into energy generation systems. So the Stirling engine, which then can convert the heat into the supercritical CO2 into electricity and power. So the cool fluid then can be re-injected to make it a cool, self-sufficient, sustainable loop. So once this is reached, then it's sustainable itself. So then moving on to the kilopower watt reactor. So the kilopower station is the primary source for geothermal drilling operations. It supplies power for the instrumentation, robotics, thermal sensors, fluid pumps, and then it also uses its power to preheat and prevent carbon dioxide brine freeze in boreholes. And a borehole is the narrow shaft drilled into the ground for extracting resources, so like geothermal extracting water or gas. So the kilopower reactor system, how it actually works, each unit is a kilopower fission reactor, and it uses the same fuel as the small modular reactor unit inside the base. So each unit has uranium-235 fuel core, which is about 1.5 meters tall, and it generates heat from nuclear fission, so similar to how which then uses Stirling engines to convert heat into electricity, which this is similar to how geothermal energy is converted currently on Earth. So per unit, which is like for one section, there is a thermal output of around 4 to 10 kilowatts and an electrical output of 3 to 7 kilowatts. So at the kilopower base at the moment, there would be a cluster of 4 units, which will totally produce power of 40 to 60 kilowatts. But looking into the future, as the base is modular and it will hopefully expand for sustainable life, this kilopower reactor unit can easily expand with it, and more units can be put in place to produce higher for more power generation. So then the linkage from the kilopower grid to the geothermal drilling unit. So the power linkage is you have a shielded high voltage direct current cables, DC cables, and the redundant lines, which are going to be buried under Mars regolith to avoid any thermal damage, to prevent overheating, which could cause damage to the cables, or any damage possibly from harsh weather environments if it was actually on the surface rather than subsurface. The high DC voltage then passes through a step down transformer. It's like how the energy grids sort of work on Earth, which would then produce a voltage of around 48 volts, which is then transported to the underground power line to the geothermal drilling unit power bus, where like then power control nodes will step in. This is already similar, so NASA's already had some exploration in this area with the power control nodes and the uses. Then finally, the safety aspect of the kilopower watt reactor is that the reactor is around 30 meters from the main power station base, which then minimizes any effect of, if there's a radiation leak, there's not that much of a concern from that because it's not going to directly affect the base, so there's enough time to get a safety system running and to shut it down. So moving up to the backup generator and power supply. So lithium-ion battery storage banks are going to hold energy during periods of low production. These are stored on the base level, level 3, near the modular nuclear reactor, which is sort of the fuel area within the power base station. So the lithium-ion batteries, they store solar energy for use during Martian night, or when power generation is insufficient due to long dust storms. So it's going to act as a contingency during unexpected power loss. Then you also have thermal energy storage, so molten salt storage systems, which are similar to those used as solar power plants already on Earth. So they can store excess energy in the forms of heat, which could be converted back into electricity when needed, like during areas or times of emergencies, or during times when power generation is low during extreme weather conditions. So the diagram on the left-hand side is the ESA Nobel-winning lithium-ion batteries powering space. So lithium-ion batteries are compactable, so they're what we use in our phones. So these are just a sort of a slightly larger scaled-up version of this. So this won the Nobel Prize for Chemistry. So these lithium-ion batteries are very energy-dense, long-lasting and rechargeable, and they've revolutionised the modern world as they're found in everything from laptops to cars, smartphones. And then they also could have the same revolutionary effect, hopefully, in space. So moving on to the power grid distribution, so key features: microgrid architecture, the power routing and cabling, the distribution, the smart grid technologies, redundancy, resilience, and that it's expansion ready, which is very important if you're trying to make a base on Mars which is independent from Earth intervention, and then also power transmission. So the microgrid architecture, the settlement will rely on modular microgrids where power generation, storage and consumption is distributed across smaller independent nodes, which was previously talked about in the kilopower watt reactor. So each habitat module and greenhouse will operate as a semi-autonomous power node, which means that this works sort of similar to how a parallel circuit in light bulbs work. So the microgrids can island themselves during faults or failures in one part to allow functioning on all the other facilities and bases and grids, even if one is faulty. So it maintains local power while disconnected and not affecting the rest of the network if there is a fault or failure. So the power routing and cabling. So you have the shielded power lines which are routed along habitat structures, and then as they're going from structure to structure in underground conduits or beneath like the Mars regolith surface, to reduce exposure to radiation and to keep it at a constant temperature to reduce overheating, which could affect then the actual power transmission rate. The moving on to 3, the smart grid technologies. So the central AI-based system management will continuously monitor the real-time power generation versus consumption, the battery and fuel levels, and will also help detect changes to environmental conditions. Load balancing algorithms to distribute power efficiently could also help reroute if in case of failures, and then also integration of LOT sensors, which have already been looked at in all infrastructure, would ensure predictive maintenance and fault detection to allow for quicker allow for quicker shorter notice to be able to fix the problem to reduce damage that could be caused. Moving on to then redundancy and resilience. So redundant cable pathing and failover systems are critical for survival during the harsh Martian conditions. So each essential facility will have its own life support system, habitat heating and communications, and it has independent backup links to power sources. As mentioned, if one facility shuts down or there's a fault and that stops working, it doesn't affect the other facilities, so they can still be running smoothly and efficiently. And there will also be use of rotational power schedules and non-critical systems throttling during power shortage to ensure each facility is getting the minimum requirement that it needs for it to be able to function. And then moving on to the fact that it needs to be expansion ready. To enable for this to become a sustainable, self-sufficient settlement in the near future, this needs to be an easily expandable design, which is a use of like the plug-and-play grid architecture, which allows for rapid expansion of the settlement, which can easily just be added to. So power nodes can easily be decommissioned or relocated, moved, which makes the grids dynamic and an adaptive system. And then the power transmission, so the DC power transmission. So Mars's low gravity and thin atmosphere makes it ideal for low loss DC power transmission over longer distances, so as the colony expands. So this can minimise the energy loss during transport when the colony becomes larger and it's surfaced over a larger area. So then here is just the power sources and the production rates versus the output. So as you can see here, the geothermal energy system requires a large proportion of power. It requires a lot of energy. So this is why that everything else takes priority over the geothermal system. So the extra energy, if there's extra or overrun, it goes towards the geothermal system. So it will be, if there's a power shortage and the other facilities are struggling to operate and run smoothly, the geothermal system will immediately just be shut down, and that can be then continued maybe when, if it's power generation is low during a long Martian night or dust storm, the geothermal system can just be shut down, and all the power from the kilopower reactor can go towards helping support the life support things actually inside the base. So the geothermal system is not the priority. It almost comes last because it's the experimental use and basis. So you need to make sure everything is running smoothly and efficiently to be able to actually develop the geothermal system further. So moving on to in situ versus transported. So quite a lot will have to be transported from Earth originally, but then when it's up and running, so you've got originally the 3D printer transported, nuclear fuel uranium-235, Stirling engines, a small modular reactor, but that can be transported as it's in compact form and then assembled on. The Teflon polymer, which is a special material that blocks the UV from the solar panels, and photochromic solar cells, because you're not sure how they would actually be put together and made due to Martian conditions. So then in situ, however, drill replacement bits like the PDC drill head can be produced by the 3D printer. So, and then Mars regolith, which comes from the Martian surface, could be used for radiation shieldings, utilising the resources Mars naturally provides. And then, the 3D printer to use to make replacements for small faulty equipment, or little things like that which need to be kept up to date. So then moving on to the greenhouse garden, which every facility, I believe, every base will have its own. So you have the structure, the oxygen production from plants, water recycling and harvesting, backup systems, food production, and then integrated life support cycle. So starting off with the structure, you have a pressurized dome made with translucent materials like polycarbonate or ETFE, but also thinking back at the experiment that's done on the solar panels, if it's how the solar panels will change the amount of light that allows through due to the environmental conditions, to due to the amount of sunlight, and due to with the photochromic cells, if this proves to be efficient, this could possibly be used on the outside of the greenhouse garden as well to maximise food efficiency and food production. And possibly an idea is because how aluminium is used, for example, after marathon runners finish a race, because it reflects external heat away, but also reflects the own heat coming off the runner's body back towards them. So possibly layers of aluminium could be put within inside the greenhouse facility to ensure like a constant temperature for internal climate control, for like temperature, and then artificial lighting and natural light, which would be the filtered solar. This helps during dust storms and Martian night cycles, so the LEDs, to ensure that the greenhouse can be self-sufficient. And then the plants to include, so the crops need to be high in edible yield and fast growing. So for oxygen production, possible crops could be algae, duckweed. For food, you could potatoes, lettuce, beans, cocoa plants, wheat, tomatoes. And then for water purifiers, wetland plants or hydroponic algae. And then regarding the water recycling and harvesting, you could recycle water from plant transpiration, human waste, condensation from air, and then also harvest water from subsurface ice or regolith, which is possibly from the atmosphere, so a closed loop possibly of hydroponics and aeroponic systems, which could reduce water use within the facility by over 90%. You have oxygen production from plants, just like photosynthesizing. And then moving on to food production systems, possibly hydroponics. So which is like nutrient-rich water instead of soil, which is controlled delivery of nutrients, which are lightweight and efficient, or possibly aeroponics, where the roots are suspended in air and misted with nutrients, which could also, these nutrients and minerals, possibly from the geothermal drilling unit into the ground, using the seismograph to detect any minerals. Possibly those minerals could be used for the aeroponic system. And the aeroponics would be quite good, as they're good for Mars's low gravity. And then the integrated life support cycle. So you have the sort of continuous humans exhaling, respiring CO2, and then the plant absorbing it for photosynthesis, which then produces oxygen. And then plants transpire water, so the water could be collected, condensed, and then reused for irrigation. and then possibly waste, so like compost or bioreactor, which can be used for plant nutrients. And then moving on to finally backup systems and sensors. So we have automated irrigation and nutrient delivery, oxygen and carbon dioxide sensors, which determine the air density and air quality, and possibly also a change in air quality is also used to detect possibly harsh weather environmental conditions coming in, such as dust storms. So this could be utilised for also other areas. And then also water quality monitors and remote air control for when humans aren't present. So moving on to the oxygen storage and production systems, the main one is MOXIE, the Mars Oxygen In Situ Resource Utilisation Experiment. So due to Mars's atmosphere being 95% composed of carbon dioxide, this needs to be utilised for efficient oxygen production for sustainability in the future. Otherwise, it's never gonna work long term. So here are some methods that possibly could be used. So MOXIE, water electrolysis. So ISRU, the In Situ Resource Utilisation Water Systems, where water is extracted from Martian ice or hydrated minerals, and then undergoes the electrolysis process, the H2O, which goes to H2 and O2. This requires energy but does produce pure oxygen, so it's a thing to look at possibly for in the future. Hydrogen could also be stored for fuel, or be used for ammonia production. And then ammonia production could then also be used for fertilizers for plants to encourage plant growth. So possibly that's a cycle that could be reused. And then photosynthesis-based systems from the greenhouse gardens, which harness plants, algae, or engineer microbes like genetically modified to produce oxygen biologically. So you have plant habitats like controlled environments with crops or fast-growing plants like duckweed, which produce oxygen and food, and then also recycle CO2, carbon dioxide from humans. So that could be a possible way to utilise waste products, human waste. So you've also then algae bioreactors like cloaca, so which are compact and efficient and can function with Martian light with extra artificial supplements such as like LED. You could have a wall of growth area surrounded, as previously mentioned, with aluminium to reflect heat and light back. That is given out during respiration to keep it as a sort of closed energy system to maximise production rates. And then some extra considerations could include the storage and distribution. Oxygen needs to be stored in pressurised tanks and then piped around to other bases, monitored with redundancy and fail-safes. And then the redundancy and safety systems, oxygen sensors, backup tanks, energy masks, and routine checks in autonomous AI diagnostics. They're accessible from all levels within the power-based facility, and then the backup tanks and emergency masks will be accessible in all bases and all facilities on the whole Martian colony. So moving on to MOXIE, so you have, which is already used by NASA. So you have the station overview, power integration, core systems breakdown, structural layout, autonomy and maintenance, modular deployment, and then the closed loop extension, which is a possible extension to increase its efficiency. So the station overview, so its purpose is for a large scale of oxygen production for fuel and breathable air, and the oxygen output goal is for a production rate of around 2 to 5 kilograms a day. So the power integration, the estimated power use for each MOXIE unit would be around 1 to 2 kilowatts. So for a sustainable future, the base will be modular, so will eventually every station will need to have multiple MOXIE units to itself, which then will require about 15 to 20 kilowatts of continuous modular. So it sources its power from the small modular nuclear reactor, and its backup is the rechargeable lithium-ion batteries. So the core systems breakdown include the atmospheric intake, solid oxide electrolyzer, the thermal system, oxygen capture and storage, and then exhaust handling. So the atmospheric intake, it pulls in carbon dioxide from Mars's atmosphere, where it then can go through a dust filtration system, possibly which could have electrostatic filters, which is then connected to a compressor, which brings the carbon dioxide to working pressure. This is then connected to a solid oxide electrolyzer known as XOXE, SOX. This heats the carbon dioxide to 800 degrees, where it then uses ceramic electrolyte to split the carbon dioxide into carbon monoxide and oxygen. So this has a high temp ceramic heating elements with an insulated reaction chamber. Then heat exchangers to preheat incoming carbon dioxide to try and create it as a continuous cycle. Oxygen capture and storage. So oxygen could be filtered and then cooled and compressed, or optional to liquefaction systems, so LOX storage. And then moving on to more of the structural layout. The central electrolyzer core, the radial atmospheric intake arms, like the regolith insulator dome, and then it would also consist of a power distribution hub to be able to make sure it's working efficiently, and then autonomous rover docking ports for tank retrieval and maintenance, which is overridden by humans in the facility of level 2 of the power base station. Then autonomy and maintenance, you have the built-in robotic arms for replacements, and then redundant components or mini parts which are becoming faulty can be reproduced by the 3D printer. Modular deployment, so it can be delivered by a cargo lander in bits, and then autonomous setup or human setup to connect each module. And then possibly the extension of the closed loop system, which you integrate with a Sabatier, I think that's how you pronounce it. It's already used within some facilities of MOXIE stations already, which uses oxygen and carbon dioxide and hydrogen to make methane, which combines with water electrolysis, and then can finally combine with a fuel cell to reuse excess oxygen for energy regeneration in like a reverse process. So then moving on to the roles on the base, you have the power station chief and the power systems engineer, which is one role, environmental and safety officer, mission systems coordinator, operations technician, automation and robotics specialist, and then a researcher. So also on the base, ideally, you want 3 female and 3 male roles. As previously mentioned earlier, the dormitories in the top level 3 of the facility, are split into female and male, and also it allows for a hormonal balance on board and gender equality. So regarding the power station chief and the power systems engineer, so their main role is to oversee aspects of the power station's operations, personal and safety. They also have a huge responsibility of leadership and oversight, so they supervise all the other staff and oversee all the energy generation systems, the monitor output and efficiency to ensure smooth continuous power generation. They also need to have like strategic planning to be able to set mission goals and coordinate long-term expansions, and a plan for energy production based on like weather patterns or new information that could be delivered from Earth to help the base colonize and grow on Mars. They also need to have a quality of decision making, so make real-time decisions during emergencies and prioritize power allocation during shortages. And then also they need to be good at reporting, communicating with the other bases and keeping everyone up to date, so send regular performance updates and reports to other bases and also back to Earth. The mission system coordinator, their main role is to interface between the power station and the broader Mars mission. So their responsibilities is to coordinate power usage and efficiency across the base and then distribution of it, plan energy consumption for critical events like dust storms, long Martian nights, and then schedule up-to-date maintenance and system upgrades without disrupting power flow. Moving on to the environmental and safety officer, their main role is to ensure safety and personnel for environmental control within the station. So they monitor radiation, air quality, pressure levels, and they also conduct frequent safety drills and emergency preparedness training to make sure everyone on board is up to date with like safety protocols and what to do in case of fire suppression, to how to deal with fire suppression, leak detection, and backup life support links and stuff like that. So it ensures proper handling and storage of hazardous materials as well, and then oversee radiation shielding to make sure it's never getting, the radiation is never actually being able to penetrate through. Moving on to the operations technician. So their main role is just the day-to-day operation and upkeep of the facility. So they monitor the control panels in level 2, systems dashboard, order robots perform scheduled maintenance like checking wiring, and they assist in physical inspections of external units if human intervention is needed. The automation and robotic specialist. The main role is to maintain the program robotic systems, which are supposed to be running the base without human intervention, and human intervention is only if it's critical and needed. So a large portion of keeping the base maintained and working efficiently is the robotic system. So the responsibilities of this specialist is to operate and troubleshoot drones, robotic arms, and maintenance bots. And then also update AI control systems that automate monitoring and minor repair units, or for adapting any new enhanced programs of AI that have been discovered on Earth to be able to utilize them and possibly integrate them within the facilities on Mars. And then the researcher, their main role is to be focused on the geothermal experimental aspect and to improve the current systems to adapt to Martian conditions. And their main aim is to try and make the geothermal unit be running as quickly and efficiently as possible, but also to make sure it's sustainable and efficient. So their responsibilities include research and development activities, energy production for Mars conditions, like to study how Martian conditions affect energy efficiency and durability. So data collection and analysis, to analyse possibly new geothermal activity and seismic activity on Mars to see if these areas could be utilised for geothermal energy production. So the next slide is the skills required for the specific roles, but then also the skills that everyone needs to be to have for any role within the base. So you have like technical competence. You're going to have to be a highly skilled individual and trained within multiple systems and multiple areas. Teamwork and collaboration. So if you're with 6 people forever, how long? You need to be able to work, communicate with others efficiently and effectively. Adaptability and flexibility, because you don't really know what's ever going to be thrown at you, and you just need to be able to deal with change and just be able to almost, as the Mars base is being expanded and becoming like going into the future, you also need to be able to almost transition with it and not almost be stuck in old ways. So multi-skills and hands-on, high responsibility and safety awareness, and also mission commitment, because you need to be completely dedicated, obviously. And then regarding the more focused skills required for the individuals, so for the power chief and the systems engineer, they'll need a high level of electrical training, knowledge of energy systems, robotics and AI, systems integration, leadership, crisis management, logistics coordination, and also familiarity with Martian environmental systems and mission protocols. So the mission systems coordinator, communication, systems thinking, logistics, being able to schedule and mission planning, and time management as well. Environmental safety officer, so first aid training, like a high level, safety compliance, environmental science possibly, be able to like respond to emergencies and knowledge of radiation protection. Operations technician, so technical and mechanical knowledge, hands-on repair, as if human intervention is needed, they'll be the operations technician will be the first human sent out to deal with the problem. And then automation and robotic specialists, so they're going to have knowledge in robotics, AI programming, remote diagnostics, machine learning, good adaptivity. And then the researcher possibly could have an advanced degree in either energy systems or material sciences. They need to be good at experimental design, data and analytics, scientific reporting, and also creative problem solving and innovation under extreme constraints. So moving on to the astronaut training program. So phase 1 would consist of foundation training, so physical and mental conditioning, Martian environment survival skills, then habitat and life support systems operations. Phase 2, which is the power system specialization. So this consists of power station systems training, engineering and repair skills, like being able to use the robotics, maintenance, 3D printing tools for part of construction, electrical troubleshooting, and also energy management, so load balancing for station power, knowing what to prioritise. Phase 3, the operational training will include mission simulators, communication delay handling, scientific data collection skills, so monitoring power generation and using analytics. And then phase 4, psychological and team conditioning, because as much of the physical aspect, the psychological aspect is just as critical and important to be able to almost survive emotionally as a base, like in a base on Mars, which is isolated. So this is going to have to be a very important aspect of the training, that they can do isolation and confinement training and also mental resilience. And then finally, transitioning period and on-site training. So during transit, there'll be a repetition of mission critical procedures, peer mentoring and support, and then virtual reality freshers of the systems. And also after arrival, you'll have habitat systems validation, so on-site adaptation to Martian gravity and terrain, and then real-time power system configuration and operation. 1 out of the 6 members of the team will need to be specially trained as a medical officer, and then all 6 members will have basic first aid training. So here is just some YouTube videos of astronaut training. So the resources necessary for a week. So the food calories would be around 2,500 per day, but everything is also going to depend on the individual, because individual needs are going to be that need to be met are going to be different for everyone. So here is just a rough outline of what could be needed. So water, drinking 2 to 3 litres a day, and then oxygen consumption at a rate about 0.84 kilograms a day. And then moving on to guidelines that could be provided to other facilities. So energy consumption awareness. So being able to monitor and optimize energy usage, to install real-time energy monitoring tools that allow all bases to track their energy consumptions, to be able to encourage energy saving behaviour, so regularly remind crew members to use energy efficient equipment and to limit non-essential power use. So similar to things that we do on Earth, like turning lights off when it's done, just adapting simple things like that could really help. And then also reducing energy usage during times when it's harsh environmental conditions. The next we have collaborative energy sharing, which is also able through the microgrid. So the interstation energy sharing, so in case of energy surpluses in one base, this power could be shared with a nearby base in a collaborative network, which reduces the need for each station to maintain a full reserve capacity. So if one base has excess energy which they don't need, and then one base is struggling, for example, there's a fault within the system, this shared use of energy will allow for sufficient and smooth operation still. And it was also maximise the optimizing energy distribution. So the established microgrids enables localized energy networks that can disconnect from the main grid if necessary to isolate problems or prevent waste, or if there's a fault detected within the system. And then finally, the dust storm management. So due to Mars' experienced frequency and long-lasting dust storms, which can severely limit solar power production, each base should have backup systems to maintain power during storms, and should also be just educated and aware of what to do. So moving on to the protocols of safety. Everyone on all bases will have a familiarity with what to do with each individual sort of problem that could cause, so fire, external damage, radiation leak. So for example, radiation leak, which could come from the nuclear reactor, so the immediate actions is evacuate the area immediately to a radiation safe zone, and then activate the reactor containment protocols for a remote shutdown of the reactor. And then the follow-up is monitor radiation levels, possibly with dosimeters and station-wide alerts. For external damage, which could be triggered from like dust storms, possible meteorites, or structural breach. So immediate actions is to seal and isolated damaged sections, and then deploy robotic repair units to assess the damage. And then if human intervention is needed, this can be done after the environmental conditions is safe for humans to go into and operate in. So for fire or thermal overload, so the trigger could be electrical fire, overheating of cables or components. So immediate actions is isolate the infected segment and using automated brake system. Then trigger localized fire suppression, so carbon dioxide or inert gas like helium. And then evacuate personnel and initiate remote shutdown. And then the follow-up to this is to vent atmosphere, because of the carbon dioxide makes up 95% of the Martian atmosphere. So you could starve the fire of oxygen just by venting. So then for communication failure, if there's like a system crash or electromagnetic interference, you switch to the redundant comms system, supposed to be a rover relay or something like that. Power loss or generation failure. So the immediate actions is to switch to the backup generator power systems, and also to notify other bases to see if they have excess power which can be used. So then notify all modules of power status and initiate load shedding protocols. And then the preventive systems could be real-time diagnostics on all power systems, and at least 72 hours of stored energy capacity for emergencies. So then the protocol for occupancy and entertainment, there could be scheduled recreational time to try and replicate a bit of normality for the crew, to recreate a bit of like something they would do at home, human life on Earth. There could also be a rotation, so 1 week someone chooses a movie night or a game or something like that. And then there could also be a virtual and augmented reality system, which allows for socialising with Earth-based family and friends, and then virtual reality spaces for possibly like simulation, like hiking, relaxing on a beach, or interactive games. So moving on to the spin-offs that can be applied directly to Earth. So the miniature nuclear, for energy and power systems, the miniature nuclear reactors, the safe portable reactors, e.g. like NASA's kilopower reactor, which are used for off-grid Earth. It could be used for remote research stations or disaster zones where there's like earthquakes a lot, or areas such as that where it's not always that easy to get energy to. Also thermal energy storage, so using Martian day and night cycles to create reliable power through heating storage could benefit to remote areas on Earth or desert regions. So environmental and climate control, closed loop thermal management, so efficient heating and cooling systems which could be reused on Earth to prevent possibly ground from overheating, possibly reducing the chances of wildfires or something like that. Regarding construction and infrastructure, the autonomous construction robots could be used on Earth for building power stations with minimal human input in dangerous zones like deep sea or extreme polar regions, or areas that are prone to frequent earthquakes. You could also use regolith-based 3D printing, which turns Mars's dirt into construction material, which could inspire Earth-friendly concrete alternatives. And then smart grid AI systems, so AI to manage the power grid with variable supply in extreme environments, so portable smart grids on Earth for remote areas of emergencies. And then you have remote monitoring and automation, so energy efficient LOT sensors could be used, which are harsh environment sensors, could be used on Earth to able to detect quicker environmental changes, conditions like seismic activity, earthquakes, possibly tsunamis, hurricanes, with like the dust storm detection. And then moving on to the technology, which could be more futuristic. So, for example, in the Olympics right now, regarding drug testing, it's done on a random selection basis, and it's invasive and is also possibly not fair. So, for example, Lance Armstrong went 10 years, he won a large number of the Tour de France's, and he was everyone thought it was a miracle recovery as he came back from cancer and won all of this, and it took them over 10 years to find out he was using performance enhancing drugs. So there are a few ways in which drug detection could possibly be enhanced. So the aim for this was for athletes competing in big events like the Olympics. This would increase fairness in sports and also be less invasive. So currently athletes are randomly picked, which possibly allows some athletes to go undetected for a long time. So the aim of this was to try and find a quick way which is able to test all athletes without having to take them off privately, or like, for example, swimmers, they're taken on poolside and done the drug test on poolside, which is also a severe lack of privacy on their department. So method one, you could use spectroscopy innovations. So on Mars, power stations could use compact spectrometers to analyse materials in asteroids, for example, or to monitor air quality, or to diagnose system faults. This same non-invasive technique could be adapted to scan human tissue or fluids to detect drugs through light reflection or absorption patterns in the bloodstream. So a spin-off idea could be that athletes wear a wristband, all athletes just wear a wristband, so it's not, people don't feel discriminated that, or they've been taken off but someone else hasn't for a drug test. All athletes could just wear a wristband that uses near-infrared spectroscopy to scan for substance use through the skin, to also avoid the use of needles as well, which is less invasive. So another method is using AI-enhanced chemical analysis. So on Mars, AI would monitor chemical interactions and anomalies in like reactor fuel or stored materials, so learning patterns of flagging issues if there's like a leak or something like that. So this AI-assisted detection could be used to identify subtle metabolite patterns linked to drug use. So for example, anabolic agents, which sprinters or boxers would typically take as performance enhancing drugs, which are banned because they increase muscle mass, they increase your reaction time, they increase recovery period over high intensity exercise. So what the anabolic agent metabolites do is they bind to the androgen receptors, which is a nuclear receptor, which binds to the DNA and moderates your gene expression, and and then this causes the presence of AAS and GH growth hormone metabolites to be shown in the bloodstream. So this allows for detection of early traces and is faster than traditional testing. So this possibly could be used in AI-powered diagnostic scanners that maybe every athlete has to walk through before entering the competing facility, that could detect unusual metabolic signatures linked to specific drugs. So if an athlete is picked up on possibly having something like that in their bloodstream, then you could possibly go to spectroscopy innovations, or then you that's how you select on who you want to drug test, because this could possibly pick up unusual sort of metabolite structures in the bloodstream or gene expression. And then finally, another possible way of doing this is through ultra-sensitive chemical sensors. This is less on the more athlete and Olympic so you use on Mars power stations, and this is used to detect traces for gas of safety such as oxygen leaks, or methane or carbon dioxide leaks in critical life support systems. So the Earth spin-off, these like hypersensitive sensors could be adapted for real-time drug metabolic detection in breath, sweat, saliva or blood, and is much faster than current lab testing. So this acts in the same way to breathalyzers, which are used to determine your alcohol level, but instead they detect drugs at a molecular level. So they detect opioids, THC possibly, or synthetic drugs. This could be another way of testing. So the summary of the Sustainable Development Targets: the geothermal energy development, which is used to ensure a reliable and constant source of energy in the future as it's being worked on. The closed loop systems such as waste heat recovery, carbon dioxide conversion to utilise the fact that carbon dioxide composes 95% of the Martian atmosphere. And then waste to energy conversion, so we can turn biological or organic waste into biogas or electricity, possibly through anaerobic digestion. So smart energy systems, it's like the AI control systems, where smart automation is used to allocate energy based on real-time needs and shut off non-essential systems during low generation to optimize heating and cooling cycles and ensure a smooth run of sustainability and living habitants on the bases, which also then use control and avoid spikes and overuse. So then modular and scalable infrastructure. So the stations are built with modular power units that can be upgraded easily, which is critical, as if you want this to become a living base that is totally independent from Earth and grow into a larger colony. Everything needs to be modular and scalable and easily expanded. So the modular and scalable infrastructure can be upgraded easily, which allows the scalable, for example, solar arrays for expansion as energy demand increases as a colony grows. And then shared knowledge and communication. So all bases connected by power distribution microgrid, which allows for sharing energy during shortages and then reporting efficiency data and distributing surplus power to other bases if needed. And that is it.